So, reminder from when we were lecturing last time? Last Wednesday, right? It was a while ago. We're in this realm of magnetic fields, right? And I show you guys two different ways to calculate magnetic fields. The first one was the Biot-Savart's law, right, where the magnetic field, right, is equal to mu naught over 4 pi, and then it's either charge times the velocity cross producted with the r hat vector, or if you have a current, is the magnitude of the current, the little segment of the current cross producted with r hat, r squared, right? So this is like a brute force way to calculate the magnetic field, right? If you either have like a point charge particle or little tiny segments, right? But then when you have to deal with a macroscopic wire, for example, right, you have to add up all those little tiny segments together, which brings up all the calculus stuff that we have to deal with. Okay. But last Wednesday, I showed you guys another way to calculate magnetic field, which is known as Ampere's law, right? Where the magnetic field dot producted around a loop, okay? And technically, this is known as a line integral, because what you're doing, let me just show you guys the picture up here, right? Is that you're following some path, right? And the part of that magnetic field that is parallel to that path, that's the part you add. The part that's perpendicular to it, you don't add because it's not actually pushing you forward. Okay, it's kind of like a little, imagine this as kind of like a river current, and then your boat is, waddling around like this. The current's only pushing you forward when the boat is traveling parallel to the current. Okay, and by current I mean water current in this case, not electron current and stuff like that. Okay. The neat thing is that, especially in this class, we're going to try to not deal with the this dot product hidden inside an integral too much, right? As much as possible, right? So we deal with cases where you have basically the magnetic field is always perpendicular to the path, therefore the dot product is always 0, or you have cases where the magnetic field is parallel to the path you're going along, so therefore the dot product is actually just b times integral of ds, which is the length of this path, right? Or this script L is how long this length is. It's not the distance between the two, it's the length you're actually traveling. Okay? So the neat thing about Ampere's law is that, well, that's the left-hand side Ampere's law. The right-hand side Ampere's law is kind of similar to Gauss's law, right? Where, right, by enclosing some current with some loop that's enclosed, right, you can actually tell how much current is going through that loop. Okay, and let's go to these pictures down here where, right, let's say you have some Amperian loop, right, that goes around these 3 wires, right? This is just cut out, right? These wires continues on, right, to whatever batteries, resistor, capacitors you're dealing with. Okay, and it's only the wires that are inside the loop that counts. The ones that are outside doesn't count, right? Just like when you have Gauss's law, the charges that are outside your Gaussian surface doesn't count, only the ones that are inside counts. Okay, and I did a little example where we were able to calculate the magnetic field inside a wire in about, well, it's still maybe like 4 lines of algebra, right? But it's much better than that crazy integral we had to do in the first week, right? Where I had to figure out, using Biot-Savart's law, a tiny segment of the wire and then integrate that, and then have to look up what the integral is because I don't memorize all the integrals in the world. Okay, so today we're going to continue using Ampere's law and see what else we can learn using Ampere's law as opposed to calculating a complicated integral. Okay, all right, so what we're going to do is we're going to try to find the magnetic field inside a solenoid. Okay, so a solenoid is basically a wire, right? But then it's wrapped around itself, kind of like a garden hose when you organize it, right? And then the current will flow through here, going like this, swirl around, swirl around, swirl around, and eventually come back out. So this little garden hose stack, right, has 1, 2, 3, 4, 5 loops, all built into one. The neat thing about this is that each loop will contribute some amount of magnetic field, but the loop right underneath it also contributes to the magnetic field pointing in exactly the same direction. So it's actually magnifying the magnetic field you can produce using the same current, right? Using the same current, but with multiple loops, you basically, 2 loops, you get twice the magnetic field. You get 5 loops, you get 5 times the magnetic field inside here. Okay, and that's what these things are used for, is to actually try to either magnify a magnetic field that you're trying to produce, or we'll see in the next chapter how to use this as what's known as an inductor, where it's actually trying to control how fast magnetic field changes, which is another thing we can control, right? Okay, it's another circuit component that is actually used a lot in electronics and computers and communications. Okay, so now let's try to figure out how we can calculate the magnitude of this magnetic field inside. Okay, so what I'm going to do is I'm going to take my little garden hose, cut it in half. Well, imagine you cut it in half, right? And now we have a little side view of it. Does this picture make sense? Okay. So remember, the dot indicates that you have current going out of the board. So the current is actually coming out and then going back in the circle and coming back in here, right? So it's doing this, 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 and so on. Okay. So by just using your right hand, you can figure out which direction the magnetic field is going to be pointing. I notice the blue arrow shows you that. If it's not there, then you can actually figure out yourself, right? So remember, to figure out the direction of the magnetic field, your thumb points in the direction of the current, okay? And then the curvature of your finger curves around the magnetic field, okay? So let's say we pick this last wire here, right? That means the magnetic field, right, is going to be going in this direction, right? Okay, that means inside the solenoid, inside this little cylinder here, right, the magnetic field is actually going this way. Part of it is kind of going this way also, right? And we're going to see how Ampere's law is going to allow us to figure out that's actually not going to contribute when you have many, many, many wires, okay? Outside the solenoid, it seems like you have a magnetic field going this way, but we're going to see that it's actually going to be canceled out by a different one when we get to utilize Ampere's law. Okay, so hopefully it makes sense that at least inside the magnetic field is going this way, right? Okay, so what we're going to do is use Ampere's law, and Ampere's law is funny, a little bit funny in this case, right? What we're going to do is we're going to draw our Amperian loop around like 1, 2, 3, 4, 5 of these wires, okay? But the loop is going to impinge into the solenoid down here, go this way, and then come out of the solenoid and come back this way. As long as it is in closed loop, right, it is a valid Amperian loop, okay? Just like Gaussian surface, it has to be an enclosed surface, right? Amperian loop has to be a closed loop. You have to, end up at the same point somehow, right? Okay. All right, so let's apply Ampere's law to this, and let's see, what we can learn. Right, Ampere's law is that, well, B dot ds, right, is going to be whatever amount of current inside, right, and times mu naught. Yeah, I think it's times mu naught. Okay. All right. So what I'm going to do is I'm going to break this line. So remember, this is a dot product between the magnetic field and some path you're traveling along, right? So what I'm going to do is I'm going to have it so that I'm going to have 4 different segments. Okay, I'm going to have one segment that's going this way, one segment going here, one segment going here, one segment going here, and let's see what happens. Okay. Okay. So I'm going to break this integral up into 4 different pieces. Okay. So I'm going to call maybe this path. Well, A doesn't work because then I have to use B. Let's put that. I don't want to use I either. Let's use lowercase a, lowercase b, lowercase c, lowercase d. Okay. So the path is going to be broken up to 4 different pieces. Path A, B dot ds along path A, plus B dot ds along path B. I know I'm writing a lot of stuff, right? Most of these are going to turn out to be 0. Okay. B dot ds, right, plus another B dot ds, on path D, okay, all of that is going to equal to our I enclosed mu naught, okay? Okay, so on path A, right, we note that, well, the magnetic field is going to be pointing this way inside the solenoid, okay? Therefore, right, whatever this line integral is basically the strength of the magnetic field times the length of that path, right? Because in this case, right, they're parallel to each other, right? So we're picking the parallel case versus the perpendicular case, okay? So path A, right, is just the strength of the magnetic field inside the solenoid times the length of A. I'm going to call that L sub A, right? Actually, it's actually defined. It's actually L. You don't need to put the A. Okay. What about the line integral of B dot ds along path B? What do you guys think that is? Zero, right? Because the magnetic field is perpendicular to that path, right? The dot product picks out the part of the vectors that are parallel to each other. So this part turns out to be zero. Okay. Right. So C is a little bit interesting, because what we're going to do is we're going to have to calculate the magnetic field that's from down here, and it's actually going to cancel out. So, but for now, just trust me that this is also going to be zero, where this is approximately zero. It's actually not zero exactly. Okay, you will see a little bit of magnetic field outside of solenoid, but it's very small. Okay, and of course, path D is going to be what again? Is zero again, right? Because that, once again, that's a perpendicular. The magnetic field and the path is perpendicular to each other. So the left-hand side here just all turns into B dot L, right? B times L, right? You don't even need to do the dot product anymore, because you just get the magnitude and the cosine of the angle between them. The angle between them is zero, so therefore you get a factor of 1. The right-hand side is kind of nice, because that's just the amount of current that is enclosed divided by mu naught. Okay. So the magnetic field inside a solenoid, right, if you just divide both sides by L, is mu naught times the current inside this loop divided by L. But the current inside this loop is actually not given to us. We're given the current, right, just the current in here. In this case, we know that the current inside this loop is 5 times the current, right? Right, because we're at 1, 2, 3, 4, 5. 5 current. That's all going in the same direction, right? But in general, we don't know that. Okay. So what we're going to do is we're going to say that, well, we're going to have to define this new quantity, okay, which is, let's see, I think what variable that the book uses. I guess I didn't write it down. I think it's a lowercase n, where n is the number of loop per meter. So it's kind of like how many loops there are per meter. It's like the loop density, okay, of that. Okay. So, oops. So the number of current that's going in this loop per meter is going to be, right? It's going to be, oops, let's go over here. Right, the number of loops per meter is actually going to be mu naught times the loop density, okay, times the loop, the length of this Amperian loop divided by L, and therefore the magnetic field actually turns out to be, oops, the current of each. Sorry about that. The current of each of them, right? And these actually cancel out, and it's actually the current that's going through the loop times just the number density, where this is the number density of the loop, how many loops there are per meter. Okay, so it's actually a very simple equation to find the magnetic field inside a solenoid. Okay, so that's sort of neat. Okay, and the direction, right, if I declare my x and y axis, right, like this, right, let's say I declare this to be my z axis, this to be my y axis, right, the direction is going to be along the k-hat direction, right? Okay, it's always going to be pointed along the direction of the solenoid. Okay. So this is using Ampere's Ampere's law to figure out the magnetic field inside a solenoid. And as I mentioned, solenoid has applications in electronics, but also in like big physics experiments. So this is a thing called those of you who were here last Friday for the physics talk, right? There are these big detector where, so for example, this is a big giant magnet. So by giant, I mean this is the size of a person, maybe the thickness of my thumb. So this is like, the height of like 10 people. And that's how big these superconducting magnet is. And they're made basically the same way. You just wrap wires around a loop. You just keep wrapping it. And then you make it about, how long is this thing? So negative 15 meters to positive 15 meters. So you make a solenoid that's about 30 meters long, about 5-6 times the height of a person. And you can have a giant magnetic field that's constant inside here. So this little color map here shows you the strength of the magnetic field inside inside here. Oops, that's a bad color. Okay, right? And they actually measure what is the magnetic field strength. You can tell that, inside the solenoid, you basically have a very constant magnetic field. What's going to happen is that as you get to the edge of the solenoid, then you have these called fringe magnetic field that's not going to go, directly along the z direction all the time. Okay, and it's sort of useful for us to make particle detectors out of it, because if you have a constant magnetic field, right, it makes things easy to calculate, right? Okay. Okay. So another big magnet is the Earth, but unfortunately, unless you are at the center of the Earth, you don't get to hang out inside the solenoid. Most of us actually only experience the fringe field, meaning the field at the edge. So Earth is actually a rotating body, right? So inside that rotating body there's a liquid part and some solid part, and then that rotation of that liquid iron and nickel, which has charge in it, is like a current that's swirling around. So that just makes a big solenoid inside the Earth. And then therefore, that's why the Earth has a magnetic field, and the magnetic field of Earth actually points down, straight down from the South Pole, and goes back up and comes back in from the North Pole. So the magnetic North Pole is actually pointed to the South Pole. The magnetic South Pole is pointed to the North Pole, if that's not confusing enough, right? The reason for that is because when you're on the surface of the Earth, let's say, you're some ship here, right? You put a compass on the surface, right? The compass needle points towards aligns itself with the magnetic field, right? And the magnetic field is pointed upward when it's out on the surface of the Earth, right? Okay, I don't know if that my little drawing makes sense. So if you have a little compass here, it'll point this way, right? And that's why we call this north, even though the magnetic field actually points south on Earth. Okay. Another application is microwave burritos. Microwave burrito also uses the magnetic fields. We're going to see the application of this when we talk about cyclotron motion. So just stay tuned for that. Okay. So in order to have cyclotron motion, right, we're going to have some way to have what's known as a magnetic force on moving charged particles. Okay. I'm just going to tell you what the equation is. Okay. It's basically kind of like the magnetic version of Coulomb's law. And of course, it's named after some other guy. His name is Lorentz. It's called the Lorentz law. Don't memorize that. Just call it the magnetic force law. Okay, it's something to calculate the magnetic force. Okay, so to calculate the magnetic force, you need the magnetic field, of course. Okay, and you need to know the charge of the object that you're dealing with. And of course, since it's magnetic, we're going to have to deal with cross products. Okay, everything on magnetic fields has to do with cross products, right? So it's actually the velocity vector cross producted with the magnetic field. Okay. Okay. And a way to calculate cross product, as you remember, I like to break things up into 2 steps. First thing you do, you figure out the magnitude, right? So the charge times the magnitude of the speed, right? Sorry, the magnitude of the velocity, which is the speed, the magnitude of the magnetic field, times sine of the angle between them. Remember that cross product picks out how perpendicular two things are to each other. Same thing as a sine function, right? Okay. That allows you to calculate the magnitude, and then you're going to use your right hand to figure out the direction. Okay, and this is where a lot of twisting of arms happens. Okay. So let's see what happens if we have a charge in the magnetic field. Okay, just some examples here. Okay, let's say I have some charge where the velocity is 0, right? And the magnetic field is pointed kind of like in this kind of into the board direction along this plane. Okay, well, if the speed is 0, well, the velocity is 0, right? Anything times 0 is 0, right? So therefore, the magnetic force is actually 0 in that case. Okay. Unfortunately, I wish I block out these answers. Okay, but let's say your little charged particle is traveling parallel to the magnetic field, right? And just remember that, right? Cross product picks out the perpendicular part of two vectors. So therefore, if they're parallel, the magnetic force should be 0 also, right? Okay. Now we get to the more complicated case where we have, our little charged particle traveling at some angle alpha relative to the magnetic field, right? Where this alpha, right, is exactly matched with what's up here as alpha, right? This alpha is you have to be very careful about figuring out what alpha is, right? It's not this angle, right? It's the angle between V and B, right? Remember when we do cross products or dot product, the angle that you're concerned with is the angle between the two vectors and no other angle, okay? So in that case, right, you can calculate the magnitude of the magnetic force by just taking the charge times the speed times the magnetic field times the sine of the angle between the two, okay? Right, to figure out the direction, once again, you use your right hand, right? If you grew up in Europe, this is actually a much easier exercise because the way they count is 1, 2, 3, right? So you do 1, 2, 3 in Europe, okay? So the first thing we see, 1 is V, so we put our thumb in V, okay? 2 is B, which is in this direction, and you're actually just concerned with the perpendicular part of it. And if you're pointing this kind of into the board, what happened is that 3, your middle finger, actually points in the direction of the force, which is pointing upward. Okay? Does that make sense? Okay? Right? So V is kind of like pointing in this direction, but then since they're not exactly perpendicular to each other, so you just kind of pick out the perpendicular part, right? And then B is kind of into the board, and then so F is up. Okay? Okay. The simplest case is if V and B is actually perpendicular to each other. In that case, your hand actually fits exactly like this, right? Okay. So I don't know. I'm not sure if it's. So this is the sign of a science major. You ever have a science game? This will be your sign. Okay. Okay. So let's do an example of this. Okay. So let's say I have some long wire, right? Meaning I can do the approximation where they are infinitely long, okay? Carrying 10 amps of current, and an electron travels at some, speed 10 to the 7 meters per second, passing at some angle, 45 degrees, 1 centimeter away from the wire, okay? What is the magnitude and the direction of the magnetic force on that electron? Okay, so the first thing we need to do is actually do the setup and draw the situation, because I have no idea what's going on by just reading it. Okay, so it doesn't tell you which direction this wire is, right? But it's maybe nice to just put it along the horizontal axis, right? So we have some wire that has some current going through it. Okay, since we have some current with the wire, we have a magnetic field that's created by the wire, so we can point our thumb in the direction of the current and then curve our hands to figure out the direction of the magnetic field, right? So over here is coming out of the board, over here it's going into the board, and it's kind of going around like this, right? Okay. So we have a electron that's passing exactly 1 centimeter. So let's just define this distance here to be 1 centimeter, right? So you can mark this is magnetic field B with the vector. Okay. We have some electron flying, zipping through here at some 45 degrees angle. So maybe like this is about 45, okay? So this is our velocity vector, okay? Okay. So right away, without doing any calculation, we can probably figure out the direction of the force, okay? With a little caveat, it's an electron. What's the difference? What do we have to be careful about when we deal with electrons instead of protons? The sign. It's a negative charge, right? So whatever calculations we make, we have to flip it afterward, okay? So remember that the magnetic force is V cross B, so you count from 1, 2, 3. 1, 2, right? So if it was a positive charge, the force will be downward. You guys see that? Right? V is kind of going up this way, right? B is coming out of the board at this point, right? The only the only way my hand can point is have my middle finger point downward, right? Okay. But since it's an electron, the force is actually upward, right? So that's the little caveat, okay? So magnetic force is actually pointing upward, okay? So we already figured out the direction right away, right? So if we declare that, oh, this is my let's make this our x-axis, right? My y-axis, right? We know right away that the force is actually in the j-hat direction right away. Direction done, okay? To calculate the magnitude, okay, right? The magnitude of the magnetic force is the charge times the speed times beta times the magnetic field times sine of the angle between those two vectors, okay? Okay. Be a little careful here, okay? And this is the trick I try to pull on you, okay? So the charge, we know the charge of an electron is negative 1.602 times 10 to the negative 16 coulomb. The speed is given to you, 10 to the 7 meters per second. The magnetic field, ooh, that was not given to us, right? Something wrong? Negative 19. Yes, you're right. You just have much better memory than me, I think. Yeah. Okay. So how do I find the magnetic field strength from a wire? Anyone remember what that is? Actually, it's right here. Right. So this is the magnetic field strength from a wire, right? So mu naught times the current divided by 2 pi times R, okay? Where R, go back down here, R, right, is this 1 centimeter, right? Is how far you are from the wire, okay? So the magnetic field strength is the current times mu naught divided by 2 pi times R, where R is equal to 0.01 meter, right? Okay, so that's checked, okay? What's alpha? This is a tricky point. I gave you an angle in the problem. That must be alpha, right? Okay. All right, I'm going to do a little side drawing here. This is the trick, so that I'm going to trick you with, right, in a test situation where you're in a rush and say, oh, there's an, yeah. Right, so the magnetic field is coming, so that's why the redrawing this in more detail is useful, right? So the magnetic field is coming out of the board, right? The electron is going in the plane of the board, but going at a 45 degrees like this, right? If I was to rotate this, let's say, right, so if I was to do my second finger like this, right? Right, the angle between them is what actually? 90, right? So that's the trick. So this is actually 1, right? So be really careful, right? The angle that you're concerned with is between the magnetic field and the direction of the direction of the magnetic field and the direction of the particle. Okay? No other angle matters, okay? I can give you 20 angles up there and none of them will matter, but so if you have this drawing here, then you can actually figure out it's 90 degrees, okay?
So how would it be boarded for it to have like an angle?
I'm sorry? worded. So let's say, right? I tell you that the velocity of the electron is coming out of the board, right? If that's coming out of the board, then it's in the same direction as the magnetic field, right? In that case, alpha is 0, then you have no magnetic force, right? Right. So you have to, so it is worded so that the the electron is passing through in the plane at a 45 degrees angle, right? That's the direction of the electron, but the magnetic field is perpendicular to that no matter what, right? Because it's coming out of the board. Because the z-axis is always going to be perpendicular to anything in the xy plane. Okay.
But how would you word it for it to be like not necessarily
Yeah. So I would say, so I think this is so I would say, oh, the electron is coming out of the board, right? That'll give you a 0. I'm not going to give you anything weird geometry to describe, right? Okay. I mean, I could write a vector equation. I can write that, oh, the vector equation is, you know, 5 meters x hat plus 6 meter j hat plus, 4 meters k hat, right? And then you have to figure out the perpendicular part of it, right? Okay. Okay. But in this little simple example, that's why I picked it, is 90 degrees. Therefore, you just multiply these three numbers together, right? And let's just do that real quick. Actually, when I say multiply three numbers together, I mean actually multiply 1, 2, 3, 4, 5 numbers together, right? 1.602, 10 to the negative 19, times 10 to the 7, that's the speed. And the magnetic field strength as the current was just 10 amp times so mu naught is 4 pi, right? This is an important thing to remember. Is 4 pi times 10 to the negative 7, right? So mu naught divided by 2 pi is actually just 2 times 2 times 2 to the negative 7. Okay, all of that gets divided by 0.01 in centimeters or in meters. So the magnetic field strength that you'll see, the magnetic force, sorry, will be 3.2 times 10 to the negative 16 Newton. Okay? Okay. When you're dealing with very small particles like an electron, that's what you expect it to be. Okay? Okay. Okay, so this is the interesting thing, right? Okay. So as you're asking also, right? What if the electron is moving upward on the page of the wire from the wire's perspective? So instead of the electron going at this angle here, right, the electron is actually going straight up. Okay? What would be the direction of the force on the electron in that case? Okay, can we figure that out using our right hand? Right? Right? So the magnetic field is still coming out of the board, right? The velocity is going up, right? Which way should the force be? Who thinks it's A, positive x direction? All right. I think you guys got tricked. Who thinks it's negative x direction? You can answer twice if you want. Yeah, you guys fixed it. Okay, because it's a negative charge, right? So I'm not going to go through C, D, and E, right? So you start counting, doing 1, 2, 3 again, right? So 1, right? 2, in order for me to be 2, I have to be doing this way. 3 is in the positive x direction, but what kind of charge is it? It's negative charge, so it's in the right direction. Okay, so negative x direction. Okay. Right. So that's how you figure out the direction. Okay. So there's more examples in the textbook, of course. As usual, make sure you go through them yourself, and and wherever deviate from the solution on this example, make sure you figure out what they did versus what you did. Okay. So the next section, I think we're not going to be able to do the worksheet because we only have about 12 minutes left. So we'll do that first thing tomorrow. The next section It's going to be on magnetic force on charges that are going to be going around a circle. This is known as cyclotron motion. But before we talk about that, I just want you guys to note what is the application is. You know, what is the use of all this magnetic force stuff, right? So one of them is a mass spectrometer, which is actually the worksheet that I just passed out that we're going to work on tomorrow. Okay, a mass spectrometer allows you to figure out the mass to charge ratio of a particular molecule, a particular atom, or a particular ion that you want. Okay, and this is who can think about like what would be useful for this, or those of you in chemistry already know what they're used for. I mean, it's useful in like, well, probably more electrical engineering if you need to make a computer chip. Why would that be useful? Anyone want to venture a guess? If you can measure the mass to charge ratio of a, let's say, a carbon atom, why would that be useful? Or the atoms in the room in this room, why would that be useful? Right, you can identify exactly what type of gas species you have, or liquid. You can even do this in liquid. Okay, and that's how you figure out. Yeah, that's how a lot of carbon dioxide sensor works, where it's figure out basically carbon dioxide. Ooh, this is gonna test my chemistry knowledge, right? Carbon dioxide. So carbon has an atomic weight of 12 AMU. Oxygen has an atomic weight of 16 each, right? But there's two of them. Right, so this will be hard math, 32 plus 12. So this will have an atomic mass of 44, right? An atomic mass unit. Okay, and if you know that, oh, I can just remove one of the electron off the carbon molecule, then it'll have a +1 charge, right? So by measuring the charge, the mass to charge ratio, you can actually figure out, you know, oh, there's a certain fractions of carbon dioxide in this room. And if anyone's interested in a mass spectrometer, there's actually one couple of doors down. I can show you guys how those work, okay? This is a big metal box, basically, but you can't really see much. But maybe I can open up the big metal box, okay? And the way this works is by application of both electric force and magnetic force, okay? Where, first of all, you know, the little ionized carbon carbon dioxide molecule, right, has a single charge on it, like +1 charge, so you have to measure that. What happened is that you pass it through this thing called a velocity selector. Unfortunately, the little picture is a little blurry. Okay, where you apply both a magnetic field and an electric field to it, and the balance of those two forces allows you to basically measure how fast this little ion is going to come out on the other end. Okay, if you know how fast this is going, you can actually calculate the magnetic force, right? Because the magnetic force, right, is just the charge, which you know. If you know how fast it's going, right, and then if you cross product it with some known magnetic field, you can exactly know what the magnetic force is, and therefore you can actually figure out how fast it's going to curve, and we're going to calculate what this curvature is before we end class today. Okay, this particular motion, a charged particle, where you have a charged particle going, let's say initially it's going straight up, okay? What's going to happen is that with these X's indicate a magnetic field that's going into the board. So if we were a positive charge, right, we're going to have this positive charge ion, right? V cross B, right, is going to create a force that's going to be to the left, right? Okay. If you have an object where you have a constant force pushing to the left, it's going to turn it, but then by the time it reaches here, right, V cross B now is pointing in this direction. If it's up here, it's pointing in this direction. If it's up here, it's pointing in this direction. If it's over here, it's pointing in this direction. What type of force is that? Do you guys remember from last semester? Torque makes objects rotate, but this is going around in a what? In a circle. What is that called? Centripetal accelerate. Centripetal force, right? So, right, when you have a charged particle moving perpendicular, right? Basically, the particle is going up. the magnetic field is going into the board, right, it's going to create a centripetal force on it. It's going to force it to go in a circle, okay? And this is known as cyclotron motion, okay? Okay, right? So once again, we're going to do another picture of a charged particle. So there's like 3 pictures of it, right? If you have some charged thing, right, that's going in this direction, right? So once again, we're going to use our thumb, and then the magnetic field is going into the board with the X's, right? The force is going to point towards the center no matter where you are on the circle, right? So in this case, the magnetic force is going to be equal to the centripetal force, right? And the centripetal force is mv squared over r. Okay, just a reminder, right? Okay, right. So the centripetal force is the mass of the object times v squared divided by r. Okay, and since the only force on this particle is the magnetic force is the centripetal force. Okay, so I think from last semester people get some of you guys, maybe not you guys, the people who aren't here anymore, right? They get confused that centripetal force is one type of motion that is caused, okay? So for example, the friction from a tire could create centripetal force. A magnetic field can cause centripetal force. Me, grabbing Anthony and pulling him around in a circle, that's a centripetal force. So any force can be a centripetal force, right? As long as it forces that object to go around in a circle, okay? So therefore, in this case, right, we're going to have the magnetic force as our centripetal force, right? So we're going to equate the magnetic force with the centripetal force, which is mv squared over r, okay? The reason that sign of alpha is not there is because, right, as we noted, right, since the object, right, the charge is moving in the xy plane, right, the angle between the magnetic field and the velocity is always going to be 90 degrees. So therefore, sine of alpha is actually going to be 1 all the time because alpha is 90 degrees. Okay, so if you solve this little equation here for r, right, let's just erase all this little scribbly stuff. You solve this equation for r, you're going to end up with an equation called the cyclotron orbit radius, right? This is how big that circle that the charged particle will kind of go around. The reason it's called a cyclotron is because what happened is that after you make a complete circle, right, that particle just keeps going. It just keeps going, it keeps going, keeps going. It keeps going in a cycle, so it just kind of never gets to escape, okay? Okay, and to calculate this, you just need the mass times velocity divided by the charge and the magnetic field, okay? Right? So the bigger the mass, right, the bigger the circle. The bigger the charge, the smaller the circle, right? Because charge is in the denominator, okay? So what ends up happening, you're measuring in a mass spectrometer, right? You actually know what V is, you know what the magnetic field is, but it's the ratio of mass divided by charge is actually what you're measuring, okay? Because you don't get to measure them individually, okay? Okay. All right, just a little bit more review from what is that called? Oscillation motion. Remember that stuff from last semester, right? Because this is a repeated motion, we can actually calculate a frequency of that cyclotron motion, and that's actually going to be an important number, okay? How do we calculate frequency? Well, frequency is 1 over the period of that motion. Does this guys ring a bell? No? I know it's a long time ago. Okay. How do I figure out the period of this motion? This is where a little drawing on the side will be useful, right? So I have some charged particle, right, that's going around in a circle, okay, right, with radius r, cyclotron, right, and it's going around at some velocity v, but we only really care about the speed, right? Right. Okay. So if you have some object going around a circle with speed v, right, the amount of time it takes for you to go around that circle should be what? We're going to do distance equals rate times time again, right? Where rate is the velocity, time is the period, right? Distance, what's the distance here? in terms of r? The circumference, which is 2 pi r, right? Exactly. Okay. So the period of this motion, right, is actually, the period is actually 2 pi times r of the cyclotron motion divided by the velocity. Okay. So therefore, the frequency of it is the upside down version of this, which is exactly here. Okay. And our cyclotron, right, we actually calculated it up here. If we plug that in here, it's just a bunch of algebra steps. Okay. Some of the steps simplify. For example, the velocities actually cancel out, right? The rest don't. And since q times b is in the denominator of the denominator, it goes in the numerator, and the rest of it just stays the same. Okay. So this is known as the cyclotron frequency. Okay. Okay. Do I have time for a quick example? Yeah, I'm just going to do a quick example. Okay. Okay. So there's a figure, I didn't copy it, but we can draw it. An electron is accelerated from rest through a potential difference of 500 volts. Okay. What is that telling you? That's telling you how much energy it gained, right? That energy is going to turn into kinetic energy, right? So we actually have to use that to calculate what the speed of that electron is. Okay. So the setup is a little drawing. Okay. So we have probably some parallel plates, right? And we have an electron that got accelerated through here, right? But we don't know what the speed is, but we do know the change in voltage across here, which is 500 volts. And we know the charge of an electron, which is negative 1.6 times 10 to the negative 19 coulomb, right? So therefore, the change in potential energy is going to give us the change in kinetic energy, right? The change in potential energy is actually Q times delta V, right? This will be 1/2 mv squared, right? All right, so let's deal with that. It's probably the magnitude that matters, okay? All right, so we have an equation that allows us to calculate the velocity, okay? And sorry if I always forget to put the capital V's for the voltage, right? And then there's a lowercase v, and then there's a capital V, right? Okay. Okay, that allows us to figure out what the speed is, okay? Once in a magnetic field, it completes half a revolution in 2 nanoseconds, okay? So that means the period of the cyclotron motion, right, is 2 times 2 nanoseconds, right? A nanosecond is 10 times 10 to the negative 9 seconds, okay? Okay. And from up here, right, we can calculate, you can use that, the reciprocal of it, as the equation to figure out what the other information, let's say, about the motion itself. Okay, so we actually want the reciprocal of this. So this is 2 pi times the mass of the electron times the magnetic field times m. Okay, and the thing they actually want is the radius of its orbit. Okay, okay, the radius of its orbit, which is actually not what we have in this equation, right? Because we don't have an r here, but we know that r, right, is actually mv times q divided by b. Okay, so let's see what we need to check off in order for us to calculate this, right? We know the mass of electron, we know the charge, we know the velocity with this complicated equation, right? But we don't know the magnetic field, right? So we're going to use this equation to figure out what the magnetic field is, and I miswrote this, right? This is actually charge down here, okay? Okay. So to figure out what the magnetic field is, right, I solved this equation for the magnetic field. The magnetic field is actually going to be 2 pi times m divided by the charge times the period. Okay, and I can plug that back in here. M v q, and then I plug in what b is, 2 pi m, and then qt on top, because this is going to be in the denominator of the denominator, and the mass actually cancel out. So speed which requires us to calculate something else. The speed is actually 2 times Q times delta V divided by M, all square rooted, right? So we're going to write that over here instead. 2Q delta V with the capitals by M. Maybe I'll just calculate this separately. It looks like it's going to be a bunch of stuff in here. So let's calculate what V is real quick. 2 times charge of an electron, negative 19, times the potential was 500 volts, divided by the mass of an electron, which is 9.11, 10 to the negative 31, all square rooted. Okay, so this speed is actually 1.3 times 10 to the 7 meters per second. So we know that. And then we multiply that by the charge, which is 1.6 times 10 to the negative 19. The period was 4 times 10 to the minus 9 seconds, right? And then we'd have to divide by the charge here. Wait, why are there 2 charges? So we don't need the charge. They cancel out. Why did I do that? Okay, and divide by 2 pi. So let's do that. Times 4e negative 9 divided by 2 pi, which is 6.28. Okay, so the radius of this thing is actually 8 times 10 to the minus 3 meters, or just 8 millimeter. Okay, so this little circle is going around, you know, in less than a centimeter, it's going around a circle. Okay, sorry for going over a few minutes. This example took longer than I thought. Okay. Okay. Did you guys do this lab yet in the lab? Cyclotron motion? Okay, so you guys will probably do that. Well, I guess not next week, after spring break. Okay, so tomorrow we'll apply what we learned about magnetic force to our little mass spectrometer worksheet. So we'll start off with that tomorrow. Okay.